In this video, we're going to talk about dynamic behavior of emitter followers. I've copied an emitter follower on this page along with two simplifications to it. The first being small signal representation, which is omitting RS because we're going to calculate gain in just a second. And the second is a redrawing of this common emitter. We went through this redrawing because it's very similar to how our DC emitter follower looked. Our DC emitter follower just replaced this parallel combination with a single RPi, and it didn't have this cap here. So if we combine RPi and CPi together such that it just makes a ZPi, and we observe that CMU is driven directly by a voltage source, then we'd expect this to behave the exact same way as an emitter follower, except that instead of RPi in our formulas, we'd replace it everywhere with ZPi, the parallel combination of these two elements. And that's handy because it means we can use all of the DC equations for our emitter follower. We just have to sub in ZPi in the right spots and we'll get the dynamic equations out. I've done that for AV here. So we start with our normal DC equation, but with a ZPi instead of RPi. And then we do a bunch of cross multiplication and stuff in order to arrive at a dynamic equation, which consists of our DC emitter follower gain multiplied by a pole zero pair. The pole and zero are closely spaced in this case, right? This is divided by beta plus 1, and this is divided by beta plus 1 plus RPi over RE, so close-ish to 1 depending on how you set things up. But beta is much bigger than 1 or this ratio. So those closely spaced poles and zeros represent the CPi becoming small enough that our gain goes from slightly less to 1 as the amplifier copies a voltage from the input to the output, to the gain becoming exactly 1 as all our current flows through CPi, and our VBE value drops to 0. So that means that our gain looks flat for many frequencies and then increases slightly. It turns out that emitter followers don't have infinite bandwidth, but most of the bandwidth reduction actually comes from CMU interacting with the previous stages, RS. But so the big takeaway, closely spaced pole zero pair, and the feed-forward pole comes from CPi shooting gain around the amplifier and eventually shutting the amplifier off. I've copied the emitter follower here again because we're going to take a look at its input impedance on this slide. However, I've modified it slightly to add a large cap at its emitter, CE. I've done that because load capacitances often make emitter followers unstable, which is a fact you should remember and beware of in lab, and we're going to see why on this slide. We're using the same definition of ZPi from last slide, and we've also introduced a new compound impedance to represent the load cap in parallel with RE and RO, so we're just kind of lumping these two elements together into a single impedance, and approximating RO as big. We can now calculate the input impedance for the emitter follower, and it's pretty easy because we can tell from the input that we have CMU going straight to ground, and that's going to be in parallel with something that looks just like our normal emitter follower. This is the same as the emitter follower derivation we did before. So we can use our formula for a DC emitter follower, but replace RPi with ZPi, and our emitter resistance with the sort of combination of RE and CE. Now, this is the more interesting impedance of these two, right? This is just a cap in shunt. And it turns out it can cause us problems, so I've labeled it Z danger. Now, you might think I'm being a little bit dramatic, because if I expand out Z danger, substituting in for ZPi and ZL, I get a pretty innocuous looking expression. The only interesting thing is that you have sort of a term in here that looks like a second order term, which is something that we haven't seen in our circuits before. And when we substitute j omega into z danger, so assuming that we have a sinusoidal signal across it, we'll notice that this second order term creates a value that's 1 minus r pi c pi r e c e omega squared, which can potentially become negative, and that in turn means that you have a negative real part of your input impedance. Now, negative impedance means your circuit's unstable. It's if you find a negative impedance that's identical to finding a pole on the right half plane, but you can also think of it as it means that when you decrease voltage, more current comes out, which you can imagine would be an unstable behavior. So if this term is big enough, it leaves us with a negative real part, and that makes the emitter follower unstable. So be super careful if you're using an emitter follower to drive a large capacitive load, because that makes this CE part big. Finally, it's worth noting that the output impedance of an emitter follower appears inductive over some frequencies. I've copied the emitter follower and its small signal model here, again with a source impedance at the input and a test signal at the output. So we calculate our output impedance by substituting z pi into our standard formula in place of r pi, and also note that the source resistance falls in parallel with c mu. So instead of just having rs here, we have rs parallel 1 over c mu s. Note that rs could be any other impedance. It's not necessarily going to be a resistance now that we've allowed our circuits to have dynamic effects. So for instance, if we were being driven by a emitter follower prior to this, we might see something inductive. Alright, so then we make a few simplifications. The first one is we assume RE and RO are big, and so we ignore them when we compare them to 1 over GM. The second is we assume the effect of C mu is small, so we ignore it. And then the third is that we get rid of this z pi by multiplying through by its denominator. So everything's been multiplied by 1 plus r pi c pi s on both the top and the bottom. That gets us to this expression, and with a little bit of clever factoring, we can get to our DC output impedance multiplied by a pole zero pair. But unlike the voltage gain, this pole zero pair is really widely spaced. So right, this is r pi c pi s multiplied by kind of a small divider, rs over r pi plus rs. This r pi c pi s is divided by beta plus 1. So our pole is at a much higher frequency than our zero is. And that results in a graph of our impedance versus frequency that looks like this, where it starts to increase at a relatively low frequency and eventually stops just at a value of rs. So down here in this flat part is our emitter follower working normally. In this region, current is increasingly switching from r pi to c pi, and we're getting less and less operation from our GM. Then up here, c pi looks like a dead short, and our output resistance just looks like our source resistance. We're looking straight through our amplifier stage. Now, over a broad range of this, though, our impedance is increasing with frequency, just like an inductor's would. Their impedance is j omega L. So our output impedance looks inductive over that frequency range, which can result in undesirable ringing, again, especially if you have large capacitive loads. So in summary, emitter followers have a wide bandwidth and a high frequency feed-forward zero from C pi. Emitter followers with large capacitive loads can have negative real input impedances, causing instability. And emitter follower outputs look inductive over a wide range of frequencies.